Hello, AP Statistics students. In this video, we're doing our last chi-squared test, all right? The chi-squared test for independence, which is sometimes also referred to as a test for association. We're seeing, is there an association between two variables, all right? Does knowing something about the one affect the probability of the other? All right, that's independence. If they're independent of each other, that means there is no association between them. If they are not independent, then there is an association. But if there is an association between the two variables, never say that one causes the other. All right, this is not a causal relationship necessarily. That can only be established through a well-defined experiment, right? So just be careful with that. Never say one thing causes another unless you've actually done an experiment to show that. So again, here is our sort of organization of these three chi-squared tests, all right? There is the goodness of fit, the test for homogeneity, and the test for independence. Now, mostly, all right, this one we don't have to worry too much about because it is different than the other two. All right, this is a one-way table, and you're seeing, does your data fit the null hypothesis, which is either uniform distribution or a distribution that's been told to you somehow. Okay, so that one is probably not going to get confused with the others because if you have one sample and one categorical variable, you can't run the other one. You don't have enough information, so you probably can't mess that one up as easily. These two, you can get confused. Well, because they're essentially the same thing. Some people do argue, like, don't even teach the difference between them. You do need to know the difference between them. But I did see some people on the internet be like, why? It is important. All right, there is a difference between these two, but not in the math. The math is exactly the same. The chi-squared test is exactly the same. There's only one calculator command for this, which we've already done, right? And so when we do this test for independence, the command on the calculator is exactly the same. It's just the wording of your interpretation of your hypotheses that are a little bit different. But the math is the same. And it boils down to mainly how many samples do you have? That's the easiest way to tell the difference between the two. If you have multiple populations and you want to see, hey, are these populations the same with respect to a variable? Is this variable distributed the same in both? Well, that's a test for homogeneity. Okay? Are these populations the same or different? But if you take one sample instead, and you take a look at two variables within that sample, all right, and you compare those two categories, that is a test for independence. You're taking a look at two categorical variables, two traits within one group of people. That then is a test for independence. You're testing, is there an association between these two traits? And so our wording is a little bit different. All right, so let's do one of these. We are doing the independence test right now. So we did a problem like this with this same context way, way back, and the book is sort of recycling it, but it does sort of show this pretty nicely. So we, in Chapter 1, read about a random sample of winter visitors to Yellowstone National Park. Each of the 1,526 visitors in the sample was asked two questions. Do you belong to an environmental club? What is your experience with a snowmobile? Do you own, do you rent sometimes, or have you never used one? All right, so Do you see how we have two categorical variables here? We're going to have two traits about these people. Each respondent, we're going to know two things about them. Do they belong to a club? And their experience with a snowmobile. We have one population, one sample, but we know two things about each person. Okay? And so we get this two-way table here. Do the data provide convincing evidence of an association between environmental club status and the type of snowmobile use in the population of winter visitors to Yellowstone National Park? So does one sort of help us predict the other? Is there an association, or is the association about the same, equal, no association? So let's take a look at some of the differences and similarities between these two. So when I take a look at these hypotheses, the null, there is no association between environmental club status and type of snowmobile use in the population of winter visitors. And then the alternative, there is an association. I guess I should put there is an association between the two. So again, it's a very equal to, not equal to kind of feel, isn't it? There is an association, there is not an association. And the null is that there is no association. Okay? So let's see, how can I sort of summarize that here? So your null is that there is no association between the two categorical variables in the population. Okay, now of course you can't say it like that, right? You want to say it the way it does in blue, but that is essentially what you have to say with context. There is no association between the two variables in the population. And then your alternative, there is an association between the two categorical variables in the population. Variables. Wow, bolt. There we go. Whew. Brutal. There we are. So those are your basic ideas there for your null and your alternative. There is no association, there is an association, but of course, always put the context in there. Context for the categorical variables and context for the population. Okay, you see how they put in what the population of winter visitors to Yellowstone? They said that specifically. All right, and like usual, the book didn't give us an alpha, so they are going to just choose 0.05. And so because this is one sample with two categorical variables, this is a chi-squared test for independence, not homogeneity, not goodness of fit. All right, independence. Are these two variables independent of one another? And so most of this all looks the same, doesn't it? Random sample of 1,526 Yellowstone visitors. All right, the random, same as always. 10% condition, it's not an experiment, so we are assuming that 1,526 is less than 10% of the population, which is winter visitors. Same as always, right? No difference there. And large counts, all the expected counts are at least 5. All right, so here, if you're doing this on a test, all right, you do need to find the expected counts. Now, you probably don't want to do this by hand, right? So you would just have to start doing the test right now on the calculator. And if you remember, you type in the observed, and it will calculate the expected for you. So let's do that really quick so we can get some more practice. So I'm going to come up here to my table. So remember, you type this into matrix. There we go. second matrix. I'm going to go over to edit. I'm going to edit A. So let's see. This is a 3 by 2. If you mess up which number goes first, well, then just change it. I always forget, but I got it right this time. So 445, 212, 497, 77, 279, and 16. All right, now remember, those are not the expected counts. Those are the observed counts. And so now I'm going to run the test, stat, tests. I'm going to go down to my chi-squared test, not the GOF, but the chi-squared, the regular chi-squared. My observed are in A, and it will put the expected into B. All right. So here I've kind of done the calculate part already, haven't I? But now that I've done that calculate part, I can go and double check my expected values to make sure they're good. So second matrix, I want to look at B, and so if I just hit enter in the home screen there, it gives it to me. So when we report this, we should keep a few decimals. Can I just scroll to the right? Yeah. So if I take a quick look here, all of those are greater than 5. So I'm pretty good. On a test, you would want to write that down. You cannot just say, hey, the expected counts are bigger than 5. You actually need to write it down, give a decimal or two, and then round it. But what's the language I have here from the problem? It says, see table below. You actually need to put the table below then, all right? But I don't think you need to see me write that down, right? Let's keep going. The do part. Now, we have the answer, right? It was on my calculator. I go stat, tests, and I do the chi-squared test, calculate. There are all my numbers. So, do I need to write out the steps by hand? No, you do not have to write out the steps by hand, but I should make a plug here. The book does recommend that you write out 1 or 2 steps. All right, the book does recommend that you write out a couple of steps, because if you accidentally typed in a number wrong here, all right, on the calculator, if you accidentally type a number in wrong, well, then these numbers, your final answer, your chi-squared statistic and your p-value, will be off some. And if you just have the numbers there, the test grader won't know why they're off. They'll assume you did something wrong, and you will get no credit for it. Whereas if you have the first couple of steps written out, you have a chance at partial credit. Just a test-taking strategy there for you. Remember, again, this is the observed minus the expected divided by the expected. So they just did the very first data point, where the observed is 445 minus that same number for the expected. Well, there I have to go to my calculator, don't I? There it is. The expected, top left, 525, which is what they got down here, right? Yep, 525. So they rounded 1 decimal, 0.7, divided by the 527. And then you just do that for each cell in your matrix there. And it's good to report everything. So the chi-squared test statistic was 116.6. The degrees of freedom, the calculator gave that to us as well, but here you can see the math. It's the number of rows minus 1 and the number of columns minus 1, and then you multiply them. And then our p-value was, I don't think I wrote that down. It wasn't there. All right, so stat, let me do this test for what, a third time? All right, so 4.82, well, that doesn't make sense, right? It's not smaller than 1. E negative 26, holy crap. Negative 26, that is massively small, isn't it? So 4.82 times 10 to the negative 26. I would recommend not using the E calculator speak. Not always a good idea on a test. But that is essentially 0, right? That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and then the 4. That would be 26 decimal points moved, wouldn't it? Look at that number. That's ridiculous. So yeah, that is essentially 0, right? Essentially 0. So our conclusion, no biggie here either. Because the p-value of approximately 0, yeah, they don't even write it out. It's approximately 0 is less than alpha at 0.05. We reject the null. We have convincing evidence of an association. All right, this is our alternative. We have convincing evidence for the alternative. What was the alternative? There is an association between the two variables. So variable 1, variable 2. They did not say one caused the other, right? One does not cause the other. We don't have any evidence of that. We have an association between the two in the population, all right? And again, say what the population is of winter visitors. But that's like the same as always, isn't it? We've written that sentence so many times. There's no real difference there. I'm hoping that makes sense. Most of this is the same, isn't it? I would just say a few important things. The word association is one of the big differences, right? You have an association between them instead of having a different distribution between populations. Okay? So really, the main thing we have to know is the difference between these two tests, even though the math is the same. All right, a chi-squared test for homogeneity is asking, is the distribution of this variable the same or different in these two or more populations? Now that's nice when it's really obvious, like you look at the US as a population, or and compare that to Australia or the United Kingdom or something, I think was our example last time. Geography helps, but it doesn't have to be separated by geography to have different populations. But is there a difference in these populations? Versus the test for independence or association, all right, is testing, is there an association between these two variables in this one population? And so it really comes down to how your observational study or experiment was designed. Did you have multiple groups and you're looking at multiple populations? Or do you have one population? I think that's really the easy way to tell the difference between the two. All right, I hope that made some sense. And our next lesson, we are definitely going to try to sort and tell the difference between these two scenarios.